Okay, great pleasure to introduce Heino Falcke, Professor Heino Falcke from Nimègue, Radbout University, who is going to tell us about the amazing discovery of the Event Horizon Telescope. Let me just say a word or two about him, if I can possibly get my smartphone to work. Okay. So he is Professor of Astroparticle Physics and Radio Astronomy and he is project scientist on LOFAR, the interferometer that covers much of Holland and many other countries and does low-frequency radio astronomy. He's also a member of the Nimègue Institute for Subatomic Physics. He is also a specialist in astroparticle physics and is a visiting scientist at the Max Planck Institute for Radio Astronomy. So he has visited and spent time at many places. He originally began his career in Germany at Bonn, and his most recent accomplishment has been as one of the principal scientist, is actually chairman of the science committee for the Event Horizon Telescope, and it's a great pleasure now to have him tell us about that.
Thank you. Thank you very much. Thank you for being here today. I know actually there's at least one or two people in the room who hear this talk now the second or third time. I apologize. So I'll use the same jokes as usually. Just pretend you're laughing. Now this is work, of course, with the global collaboration that we've done. In Europe, we had a team of a few institutes who've been involved, most notably, of course, the IRAM Institute in Grenoble, and which is a German, Spanish, French institute with headquarters in Grenoble, the Max Planck Institute for Radio Astronomy in Bonn, the University of Frankfurt, and Max Planck and our university in Nimègue. Of course, always confusing to have this J in the middle. Just ignore the J. If you see that in the Netherlands, just say Nimègue, and then you're fine. We benefited a lot actually from this ERC grant that we received in 2014, ERC Synergy grant together with Luciano Rezzolla, Michael Kramer, which I think was the single biggest grant given to the work on the Event Horizon Telescope, and was a big help for our efforts. And of course, the Event Horizon Telescope is, as I said, a collaborative effort. This is a picture of the scientists involved, at least a large fraction of them, 120. This was our last, in fact, only collaboration meeting since we formally started the collaboration. We actually formally signed the collaboration agreement in summer of 2017 after we had done the observations. And this was the collaboration meeting in Nimègue, about 120 scientists, officially I think about 200. And these are the European institutions, the US institutions here, Canada, Mexico, and the Asian institutions. Plus, of course, a lot of individual members who joined us and were very important. So there are 13 stakeholder institutions, but lots of individual members. And so it's still possible for individuals to join and to participate in the effort. So it's not a closed shop in general. And you've seen, of course, all the big results, I think. So I'm not going to show you anything new in the sense of the final result. If you've read any newspaper anywhere in the world, then you probably have seen it somewhere, that image. This was quite amazing feedback that we had after the announcement in April in Brussels. We had these parallel press conferences in Washington, in Brussels, but also other places, Santiago and Tokyo and elsewhere, which really showed it was a global event. What I had underappreciated was sort of what black hole means to people. We thought we had a nice image, but it was really a very emotional reaction that you got from people. People really said they were moved. They were, it's so much emotion that was associated with it. And I think this was not just about science, it was also about what black holes means to people. It's maybe something, some mysterious objects or the end of space and time, which you finally had an image of, right? Something dangerous, and now you can look at it. And so that was really, really amazing. The press conference in Brussels, there were, I think the tweet they sent out was their most popular tweet ever, compared to all the other tweets of the European Commission. So it's so science does something good sometimes in Europe. And of course, people embraced it a lot. I always said, we used the world to make that image. We gave it to the world, and the world embraced it and did a lot of things with it. This is a slide that Sarah Markov put together here, sort of, so it went all over the world. Like cats and black holes are really, really, really popular. Cats. So it's anyway. So back to science. Of course, why is it scientifically important? We want to study GR at the most extreme limit, getting as close to the event horizon as possible. This was sort of always my dream. And the event horizon, as you know, is fundamental for various reasons. One is that it sort of presents really a limit of how far we can go with our scientific studies. I mean, it's a bit weird if you think about it, that you have an object which is physically there, which was existing at some point, right? Like a star that was there. It collapses, it forms an event horizon, and then suddenly the inside is shielded from our possibility to observe it. So there is a fundamentally inaccessible part of the universe right in the middle of our observable universe. And that in itself makes it weird. And then the second aspect, of course, of black holes and the formation of event horizons is that this is where all the problems happen with quantum physics, right? If you want to, typically, general relativity and quantum physics, they live happily next to each other. We use them both, we use them in our cell phones and everywhere. But at the edge of black holes, at the event horizon, you have a fundamental problem with issues like Hawking radiation and information loss. That one of the theories doesn't really, needs to change somehow in a fundamental way. Many people think that GR and space-time is now emerging, should be emerging from quantum physics, but maybe that's wrong. Who knows? So I think we need to study this, and we need to get as close as possible to the event horizon in the long run. So how do you see black holes? And this is actually something that goes all the way back, as I noticed only 2 years ago, to my own shame, to David Hilbert, actually, who described light bending around a black hole. Well, he didn't even know that it was a black hole at the time, right? So you had GR being worked out in 1915. Then 1916, you had sort of the Schwarzschild metric. At the same time, Hilbert gave a lecture on how light would behave surrounding a black hole, or in the Schwarzschild metric. And then what he pointed out that light will be bent in the curved space-time of this object. And okay, that's what you see here. This is actually from a book by van Lauwe in 21, where he sort of depicted this. And then there is a sort of magical radius where light will be bent and actually in the asymptotic limit will be bent onto a perfect circle. So when you come within this separation here, which is at a separation of 3.5 square root of 3 Schwarzschild radii, or diameters square root of 27 Schwarzschild radii is maybe better to remember. The light will go on this path. It will actually circle forever and then stay on that photon orbit. And the photon orbit will be on 3.5 times the Schwarzschild radius. So 1.5 times the event horizon in the Schwarzschild case. You have this photon orbit where light will go on a closed circle. If light will then come within this region, will actually go inside the photon orbit and disappear in the event horizon. If it's slightly outside, will actually go to infinity. Which means the visible cross-section, so to speak, for light from infinity of a black hole is not the diameter is not 2 Schwarzschild radii, but it will be 5 Schwarzschild radii, right? So light from larger out will be bent towards the center. This was very well known, but often forgotten. And then if you go back to sort of the 70s, suddenly black holes became very interesting, again, because of quasars being discovered, and black holes were one of the ideas and models to explain the huge luminosity in the centers of quasars. What you see here is a calculation by Cunningham and Bardeen, where they looked at how does an orbit of a star look like as it goes around a black hole. And you see sort of how the light bending actually deforms that highly inclined circular orbit into this structure. And this is something that really, determines our picture of how black holes look like. If you look at sort of textbooks and other examples, this is typically how black holes are being portrayed. Nimègue calculated that in 79, actually with a computer, and drew it by hand. You see again sort of this flat disk here, thin disk idea, and then a lensed region here. See also a dark region here, which actually a large fraction of that comes from the fact that in these old models of thin disks, the matter would extend to the innermost stable circular orbit. This is the innermost orbit where matter can still be stable. Then the idea is that matter would plunge into the black hole, not radiate much. So you'd have sort of a hole in the accretion disk, and then that would be lensed and deformed. And then here you'd see sort of a secondary, a tertiary ring of the inner edge of the accretion disk going around the black hole. If you look at interstellar, for example, it's pretty much still the same pictures we have today. Now, I was working on the center of the Milky Way in the 90s and trying to explain the radio emission there. One of the things we realized was that the millimeter wave radio emission would come from very close to the event horizon. In fact, the idea was that we were using the jet model that actually the black hole would be engulfed by an optically thin emitting region inside the ISCO. Maybe stabilized by magnetic fields, maybe where the jet is being launched. In fact, that's what we see these days. This is sort of what's happening. The magnetic field are being launched. And then you have actually a thick wall or fog region surrounding the black hole. So it's illuminated from all sides. And I was at the Max Planck Institute, as you said, for radio astronomy, where they were doing the first VLBI experiments, going to higher frequencies. But then we were talked about it, and we realized, it's great, the emission comes from near the event horizon, but the black hole is still too small to be seen. We just calculate, 2 Schwarzschild radii, and then look at what the angular diameter is, and the Earth was just a factor 2.5 too small to see. But then I hadn't read, the paper by Hilbert or the lecture. I hadn't been at the lecture from Hilbert in 1916, so forgotten about it. But then saw this paper from Bardeen, which was a little conference paper written in the 70s, Les Astres Occlus. What he calculated was actually a binary system, and a black hole going in front of a star. So it resolves the stellar surface and would see how a black hole would look like. This was a maximally rotating black hole, so a really, really small one. So the diameter would be 1 Schwarzschild radii. So the radius is 1 gravitational radius, so which is half a Schwarzschild radius. So that's what you would calculate just from the size of the event horizon. But the hole it would punch in the black hole in the visual appearance would be much larger. And interestingly, even for a maximally rotating one, you would still have something which was of the order of 5 Schwarzschild radii in diameter. Why is this? Well, light, you see this is very asymmetric picture. You will see that light on one side is captured much further out than the other side. Well, that's quite obvious because the black hole can rotate, and so the light can go with the spin of the black hole, and actually it takes the space-time with it, can go much closer than as you have to go against the spin of space-time on the other side. So one side will be larger, then will be smaller. If you turn down the spin of this black hole, the entire thing will shift, but it will only gradually, will only become larger by a few percent. So whatever the spin is, you'll always have that, that dark region. And so we then calculated with this situation, we used some, we tried to be very agnostic about the emission around the black hole. We took a black hole. Now we placed the emission really surrounding the black hole using some analytic prescription, in this case here, around a Kerr black hole and with a 1/r profile of the emissivity. Or we take here a jet model, which actually was a hollow cone jet model even. And what you see is, once more, you find this dark region of about 5 Schwarzschild radii. Whatever you do, you always see this in all circumstances. Sometimes a bit more pronounced. Sometimes, if you look at from the side, it's actually going to be much more sort of one-sided. But overall, this dark region was there. We call it the shadow of a black hole because it's not the black hole itself, right? So we cannot call it the black hole. It's also not a silhouette because it's really light coming from all directions, so it's shining from all directions. So this region is not completely dark, for example, right? It's filled with emission. It's not also completely outlying the region because if you look here, for example, you see sort of the dark region here, but it actually extends slightly larger and depends sometimes to where the emission region is. Now, if the emission region is somewhat larger or smaller than the photon orbit, then you get slight deviations from the overall size that you would measure, right? So mathematically, it's well determined where this ring is, but in practice, emission coming from slightly different regions will blend this. So it will be a bit of a not perfect shadow. What we also pointed out is there is this ring of emission here that you see in this case. That is mainly dominated by this photon orbit, right? So most of the emission that generated near this black hole will be forced to go near this photon orbit. Will not be exactly on it, but it will be slightly to inside, slightly outside. Most of the emission everywhere will be bent towards this orbit, go around, and then actually pick up more emission. So it will actually be brighter. It has long path lengths through that emitting gas. So you will get a bright emission region. And it will also be asymmetric if the gas is rotating due to relativistic beaming. So you expect something like a sickle or half a crescent emission. And the size was that for the galactic center, that should be 25 to 50 microarc second. At the time, the black hole mass was uncertain by a factor of 2. And M87, the black hole mass, was actually would have given it less than factor of 20 microarc seconds, so not resolvable at the time. That has changed because the black hole mass of Sagittarius A star and M87 has grown enormously in the galactic center by almost a factor of 2 since my PhD, and the M87 a factor of 3 even, which is quite an enormous development. And of course, today we do much more sophisticated simulations. This year's simulations by our colleagues, Luciano Rezzolla. You start with a torus of emitting gas because you don't want to just do an analytic prescription of the emitting region. You want to really derive it from first principles. You start with a torus of gas. You do a GRMHD simulation, general relativistic magneto-hydrodynamic simulation. So you use fluid dynamics with magnetic fields. You use poloidal magnetic field components. You let it differentially rotate around a black hole, and then the magnetic fields will be twisted into a spaghetti bowl, so to speak. And if you continue going, what actually happens is that as the gas gets close to the innermost stable circular orbit, the magnetic fields are actually forced to go out of the accretion flow, and you actually eject a jet along the rotation axis of the accretion disk, not necessarily along the spin axis of the black hole. Because we see that we also do simulations where you misalign the accretion disk with the spin axis of the black hole, and what you see is the jet will actually go with the spin axis of the accretion flow and not the black hole. Now, the next step you have to do when you do these simulations, and these take actually large supercomputer simulations now, you also need to add ray tracing. So what you do is you have to calculate what is the emissivity, what is the temperature of the gas, What's the electron distribution function? And this is the biggest uncertainty in calculating images. How are the electrons heated near the black hole? We take some simple parameterizations for that, mainly assuming it's a quasi-thermal spectrum and has a certain temperature relative to the proton temperature. The proton temperature we can follow reasonably well. And then, this is a simulation done by Jordi Davila. You see here now multi-frequencies actually put together. We used an interesting color scale. So you see the jet actually not very prominent, but it's more like a smoke trail here. And we're focusing on the emission from the accretion flow. You can see this. So that represents more what people expect to see in terms of color scale, not necessarily what you measure with the radio telescope. You see the turbulence. You see the crescent shape here. You see the shadow in the very center. Of course, as I said, these are multiple radio frequencies that we calculate here. So you also see absorption, self-absorption by the disk. So not from all sides you would see this. You have to go to high frequencies to actually zoom into the central region. So radio emission is almost like an X-ray. So the deeper you go, the higher you go in frequency, the deeper you can go inside. And so here you see the jet, nicely being produced. Now, as I said, we were talking initially about the galactic center, but then M87 became heavier and heavier, so we included this in our thinking as well. And this was sort of the, I'm a radio astronomer, so I use the radio name. This is Virgo A, or 3C274. This is 1,000 times more distance, so actually 1,500 times, 2,000 times more distance than the galactic center, and 10 to the 5 times a higher accretion rate than the galactic center. But if you look at, this is another aspect of our work, is this fundamental plane of black hole activity. If you look at how radio emission changes as a function of mass and accretion rate, then you have typically a flat radio spectrum. From your side, you go from low frequencies to high frequencies. And then you approach closer and closer to the black hole, and then it cuts off with an optically thin power law. And that region where this happens, this turnover, this is frequency, this is intensity. Where this happens, this gets close to the event horizon. That depends on the mass and the accretion rate. It's never always at the same frequency. Okay? If you increase the accretion rate, the entire spectrum will go higher in terms of intensity, but also to higher frequencies. But if you increase the black hole mass, then you cut off the spectrum at longer and longer wavelengths, and then the peak of the spectrum will move to lower frequencies. And so depending on where the black hole mass is, it can be anywhere in this, phase space. And just this combination of factor 1,000 times more mass and 10 to the 5 more accretion rate makes it that for the million solar mass black hole in the galactic center and for the billion solar mass black hole in M87, they both have exactly the same flux around 1 Jansky here at Earth, and they have the peak in the spectrum exactly at 1 millimeter, and so that's where you have to look in order to see down to the event horizon. It's a pure coincidence. And if you also look at sort of the size of this emitting region, is about between 20 to 50 microarc seconds. This is exactly what you can still resolve from the Earth, because the Earth is just large enough with a global interferometer. The resolution of an interferometer is lambda divided by d. Lambda is given by physics near the event horizon and by the atmosphere, because if you go too short with lambda, you can't look through the atmosphere anymore. So there's a maximum lambda you can really reasonably do from the ground. And the d is set by the Earth. Right? So these are just properties of the Earth. Lambda over d to some degree are set by properties of the Earth. And it just happens to be exactly the parameters that match the properties of the black hole physics in M87 and Sagittarius A star. Pure coincidence. Now M87, this is elliptical galaxy. There was prediction of 3 billion solar masses and 6 billion solar masses. 3 billion was predicted based on the gas dynamics. And 6 based on the stellar kinematics. And there have been paper in 2013 that have been really trying to resolve that discrepancy, and they were not able to say which one was right. It was just this systematic factor of 2 was remaining, while the statistical error was actually much smaller. And so it's still not clear what exactly causes that systematic difference between those two measurements. The radio source has been studied very well. In fact, the very first AGN ever detected was in M87, 1918. There was someone found a very little white streak in this galaxy, which we now know is this jet in M87. This here is a LOFAR image, the large-scale LOFAR image, which is 200,000 light years across. You fill the entire region with the radio bubble. You see the VLA jet, which is very well known. The VLBI jets at centimeter waves. And very nicely, you see this edge-brightened structure that is seen here in these jets. It's one of the few jets that you can actually be nicely resolved in the universe. And this here is the shadow size that you can calculate, right? So that's 3 millimeter. That was the highest wavelength done until 2017. In fact, this was published in 2018 only. These were simulations that we had done. Dexter did the simulations here in 2012 of the innermost regions, and we had here the jet model developed further using parameterization we now still also use for inside the EHT. You see the jet going out here, and what we use is that we say the electrons are coupled to the protons in terms of heating based on the magnetization. If you know a little bit about AGN physics, people have been talking about evection-dominated accretion flows, ADAFs, so that you have an optically thin accretion flow onto black holes. And then you calculate how do the protons and electrons interact in this accretion flow. If you look at the Coulomb interaction, is that the protons and electrons hardly ever meet, because the gas that we actually look at is very, very tenuous. Right? It's ultra-high vacuum. Everything we see here is ultra-high vacuum, right? We think of this cauldron of fire, but it's really, first of all, you will die of suffocation, right? Because there's nothing there. And so the protons and electrons will hardly ever interact. The protons carry the kinetic energy, they become hot. The electrons will drag along, but will not necessarily become very hot, okay? And we said then, okay, if we make the heating, the coupling protons and electrons as a function of magnetization, then the situation will change. In the accretion flow, the electrons will still remain behind the protons in terms of heating. But if you go into the jet, which is completely magnetically dominated, they'll become magnetically coupled. Protons and electrons will have the same temperature. And that will actually make that you actually look at like 3 millimeter or 1 millimeter, you'll not see the accretion flow, which has many more electrons than the jet. Only a few % of the particles will go into the jet. But the electrons in the jet are going to be much hotter. You're also going to have non-thermal particle acceleration. So that explains, why we see we can use the same simulations, but if we do this, we actually are dominated by jet emission, as is the case in M87. And you also see that we see the edge being brightened, and that's because the magnetic fields go out, and they're actually pointing flux, right? Pointing flux you cannot see. You don't see the magnetic fields, you see the particles. And so as you go to the edges, actually it will drag along particles, and then you get sort of a sheath layer which will become hot, and you see. And they're very nice, and that almost comes out from first principles here. The only thing we put in is this magnetization heating of electrons. And you see this nice edge-brightened structure here, and you see this hourglass shaped here. I've used then 230 gigahertz. This is higher frequency. If you go to 230 gigahertz, the prediction actually before we made the observations even, that was a prediction at 230 gigahertz. You see the ring dominated again by this lens photon ring and the shadow in the very center. Now, of course, we have to do the experiment. And as I said, I grew up scientifically in the 90s in the Max Planck Institute, where they did the first successful detection of a few AGN at 1 millimeter, first science observations. This is Sagittarius A star observation with the IRAM telescopes, Plateau de Buhr interferometer, which is now called NOEMA, and Pico Veleta. The short baseline, but actually turn out the measurements they made was actually spot on in terms of size measurement. They actually found that the emission was larger than we had predicted in terms of short-shirt radii, but that was in the end turned out to be because the black hole mass was too small. and the error bar was still pretty large. So the measurement they did in the 90s of the size of Sagittarius A star is actually compatible with the measurement we have today, and that was done later here in these also very important measurements at 1 millimeter in the US with Karmar, SMTO, and JCMT by Dolman et al. In 2008, which gave better size measurements and also closure phase measurements. And so that confirmed essentially that indeed the emission at 1 millimeter, as predicted, came from very small scales, and that this should work. Then we have, I could talk at length about the next paper here about 4 stations, but let's continue on the 2017 experiment that we did with 8 telescopes on 6 different mountains. For the first time, really, in this large array, including South Pole. First time I say Pico Veleta as well, because in the years before it had actually either bad weather or something else. Usually it was bad weather, I think. Alma was included for the first time. That was the important thing. LMT in Mexico. Karma, unfortunately, had been decommissioned. Hawaii, SMA, and JCMT, and Apex here as well. The data actually was correlated in 2 different correlation centers, independently at Haystack and Bonn. So we split the data in 2 and sent it to 2 different locations. And the amazing thing that happened in 2017 is that we went to the telescopes, and usually things go wrong the first day, or the weather isn't good, you have to wait. So we usually have a 10-day window, and we hope to have the high priority data at the best weather day. The weather has to be good all around the world, because 1 millimeter waves are significantly affected by water vapor in the atmosphere. You have to have a high dry side to do this. And it turned out, the first day the weather was perfect. We started observing. The second day the weather was perfect. Third day the weather was perfect. We were actually very relieved that there was some bad weather, a few scattered clouds in the next 2 days, so we get some rest, because some people, especially the crew in Arizona, they had to work 16, 17 hours shifts. They could have done it more in turns, but they really wanted to do that all, right? So you know how you are, right? You don't want to miss an hour of the observation, really. We recorded about 3.5 petabyte of data. And except for some minor hiccups, actually data was pretty high quality. So this was very amazing that, the first time we had this large array of telescopes assembled, we also had perfect weather. In 2018, we redid this observing run, and we had, bad weather. At Pico Veleta, I couldn't see the top of the dish anymore, even from the control building. It was so cloudy at some nights. In Mexico, there was a security incident. So we had to actually stop the observation. So 2018 was much, much worse. Much more normal, I would say, in a way. So these are the pictures of the telescopes and some of the crews. We actually had 4 or 5 people sent to each telescope. I was actually here in Spain. I always say because of the good food there. So it was because they cook there for you. So it's nice. This is the equipment that we had. This is the VLBI equipment. Actually, a lot of that was a lot of European contributions here for Pico. It was, I think, purchased by Max Planck. For many of the others, it was purchased by the ERC. And then there's also an NSF grant, which covered then the rest. So that's how most of the VLBI equipment was bought. You have a maser, an atomic clock in the basement, which I don't show here. You have ADC converters here. You have filter banks, which down-convert the data from the frequency, or couple the radio frequency from the telescope to the AD converter. And then you have these hard drive racks here. So each of these boxes here you can take out actually contains 8 hard drives of 6 or 8 terabytes. And they're recording 32 gigabits per second. That's why we can't use the internet. People always ask, why don't you use the internet? Well, 32 gigabits per second from the South Pole is not really working. Not even from Picovolata or most of the other telescopes, right? I think there's not a single telescope has a 32 gigabits per second internet connection. And the next year, 2018, we did 64 gigabits per second, doubled the bandwidth. This sort of from a VLBI monitor online tool that we built, which actually gives us the weather information and status information from all the telescopes online. So all the telescopes give their information. And you see here actually how the targets move over the Earth. Actually, Earth moves under the targets. And then, but you know. Yeah, I always have to correct myself, but you know. And then we're switching back and forth. So this M87, actually a northern target. Actually, we cannot see it from the South Pole. But then we have 33273 and 279, which are nearby. And then we can observe those with the rest of the array. And that was important because what we're doing is we're calibrating the data. You have to calibrate each telescope. Each telescope has its own personality. And we're doing the calibration only on 273 and 279 first in order to actually get our calibration properties and procedures right. And only then we looked at M87. And that happened then, actually took until, from April 2017, the data arrived in December, the South Pole data arrived in December 2017. We had done some preliminary correlation with the other stations and did a recorrelation in January, February, a iteration based on these other targets. And then we had this first results from the calibration team, which actually was a very small team of 5 people from Harvard and Radbout, actually. And what you see here is the baseline length, is the visibility amplitude. The visibility amplitude, what you do in an interferometer, you actually, as you know, a telescope, the mirror in a telescope actually does an analog Fourier transform, right? If you go through a mass of a telescope, in the mirror does the Fourier transform. And so what an interferometer does, it measures the data in the plane where the mirror is in an optical telescope. And as the Earth rotates, you measure different components of the Fourier transform. And so what we measure here is Fourier components, amplitude and phase. That's important in a radio interferometer. And what we plot here is a phase, now in a 1D plot, so the 1D Fourier amplitude. And what you see here is a null here and a second null here. And that null is something, if you're a radio astronomer, you know immediately what this means. Actually, you think this is a ring or a double source. You know, it could have been both. But you know, the location of this ring actually gives you the size. And immediately it was clear this was about 40 microarc seconds. So when you see this, you get very nervous. You haven't made an image, but this is a 1D plot, so you still have to make an image. And so that's the next step in the entire process. Then there was data reviews that was passed on to the imaging team, and people did the imaging. All right, this shows how interferometry works. So here you have essentially one baseline, and it's you actually get a fringe detection, a double slit experiment, and then you get a fringe pattern here. And the amplitude visibility is the strength of that fringe. How well is it correlated? If you have a point source, then you get 100% correlation between the data. If the source is extended, you get uncorrelated emission, and then you don't see a fringe. Okay, and then changing the variability amplitude. And so we now let the Earth rotate, look at the galactic center, and try to see how it looks like. And then, by adding more and more components, you find it looks like a teapot. Okay, well, okay, good. Well, anyway, so it's a bit surprising, but you should be open-minded in science. Okay, that's how it works. Then we're looking at the galactic center, and this, of course, I have to show. I show this nice movie here. Of the zoom into the galactic center, and so we did the imaging. I show the result first, but I like the zoom. And the music was from my son, so. It's the LOFAR image. This VLT did actually an optical image just for us. Jet, the optical jet. Yes, a little bit of drama sometimes. But of course, this is not the first thing you see. This is the last thing you see in the entire process, obviously. And so the first thing we did was actually, right after the calibration data was done, to split up into 4 individual teams. Actually, some were really mixed. Team 2, that's where we participated, was actually Haystack, Radbout, and Japan. So really mixed together. Here's 2 of my students sitting there. Sarah Isaoun, who really, and Freg, Monica from our department, and some Kazu Akinori here. Akinoro? God. And so the data was given out, and essentially in the night, all the teams made the first images. So it's not that one person made the first image. It was really made around the world by many different people at the same time. And then for 1 week, they had to interact with each other, and then make an image, and then submit it, and then compare it. And these were the first 4 results. And you see, all of them get ring-like structures. And so that's an experiment you can only do once. The reason is, if you do these imaging algorithms, you have to always take out the artifacts, because we only measure incomplete Fourier components. It's like you make an image with a mirror which has scratches everywhere, right? Your point spread function gets completely deformed. Okay, you have to sort of clean that image, and that has parameters. And so you don't want to fool yourself, but that was a good first test. And then now we went back to actually do a systematic study of imaging algorithms. We started with simulated data. We started with a ring, crescent, a disk, a double source, as I said before, or a GRMHD image. And then you pass it through different imaging algorithms and also different parameters. A wide parameter study was chosen. And we chose the algorithm and a set of parameters that were able to reproduce all these images reasonably well. Okay, so if it's a disk comes out. If it's a ring comes out. If a double source comes out. So you don't want to be fooled, essentially, by what you want to get. You want to sort of do this as agnostic as possible. And so that's how we determined the parameters for the imaging algorithm. This was all scripted, and then made the final images with different tools. This is DiffMap's actually clean algorithm, which is 40 years old or 50 years old by now. It's a standard VLBI tool. And these are maximum entropy methods. One developed in Harvard, and the other one here developed by MIT and Japan. And all 3 actually gave comparable results. But you also see subtle differences, right? You see this one being brighter here than here. And so the intensity distribution along the ring is sort of somewhat dependent on the choice of parameters and code. And also, but the size, for example, the size of the ring is very, very much the same all the time. We had 4 different days, and that was, to me, most important. We actually had 4 really very independent data sets, and we always got the same results. Also, the UV coverage was slightly different, so we got the same results. And then actually the question was, how do we combine the different things, the different algorithms? In the end, we went for one day and just combine the 3 algorithms into one. It's not statistically, there are lots of discussions how to combine different algorithms. There's no good solution to this. So, this was the easy one. Now, I would say we have a lot of tools that we developed. A lot of them actually we developed within the ERC project also. We have an automatic VLBI calibration pipeline. We actually have VLBI in CASA now, which is a standard tool that people use in astronomy. We have HOPS, that is another one that was developed at CFA and MIT. We used both of them. We did everything we did twice or 3 times. We had multiple imaging algorithms. As I said, we had multiple plasma simulations, actually 3 different codes. We had 3 different ray tracing codes that we also compared with each other. And actually, at least the one that we developed in black hole cam can do arbitrary spacetime. So we're not only doing black holes, we also do whatever boson stars, neutron, and other things. We have a VLBI simulator that was developed, actually 2, and we have multiple parameter extraction software. We also did simulations. This year is a simulation, we had big simulation library. This year is a simulation at 230 gigahertz. You see the nice photon ring here. Actually, sometimes double or 3 times. That depends on where the emission is. So you see it's not exactly sharp. It's it has a little fluctuation around here. And you see sort of the rest of the emission. So that dominates the emission, but you still have emission elsewhere, right? The shadow is not perfect. And that's important if you want to fit the data. And it's turbulent. And so, one one best fitting image of the simulation library doesn't necessarily mean this is the best model. This is because this is a turbulent thing which changes from day to day. So this is something you have to take into account in the physics. So this is the image library. I should have changed the slides actually in order. So we have 60,000 snapshots of images that we made for different orientations, different parameterization of the heating, different spins and everything, and compared them to the data. And trying to take into account this, the uncertainty based on the turbulent emission. Now, this is sort of the one thing that you see. They all have rings, they all have shadows. And from the size of the shadow, you can determine what the mass is. And we used 3 different methods, and what we find is, I'm not explaining this in detail, this is a black hole mass. These are 3 different methods to extract the black hole mass from the image. And that's actually all 3, and these are mainly dominated by systematics, not statistical errors, give 6.5 billion solar masses. So really quite consistent with the stellar kinematics and at most marginally consistent with the gas dynamics, if I want to be polite. The people ask about the spin often, and we purposely put this into the paper because this is a negative, no spin, and positive spin model. And they all have the same size rings. And they all reproduce the data very well. So at this point, we're not very sensitive to the spin. That will come with polarization and variability, probably. But at this point, we cannot distinguish between the 2. This is another one we haven't shown in the paper. These are the 2012 and 2016 predictions, and now run through the simulated observations from 2017. So this was really published before. This is using our simulation. I think this is an amazing prediction that was made. And the reason is, in the end, GR is simple. the shadow and the physics of the ring and the shadow is relatively straightforward. And so I think this is, to me, actually the most amazing image. We've done some more simulations, not geared towards M87 previously. We've run non-standard spacetimes. This here is a dilaton black hole. So you take out the spin, but you add a scalar parameter. There's some axion-inspired models for this. And you can actually image this still has an horizon, but it's a black hole with a different property. And actually, the ISCO and the photon orbit are different radii. That's the difference. But you can, by adjusting some parameters, if you have enough free parameters, you can make a dilaton black hole look like a Kerr black hole. Yeah, this one is non-rotating, but has a high scalar field, a dilaton scalar field, and this one is highly rotating and has not. And they still look very similar. They look different in detail, but in order to see those differences, you would have to go into a higher resolution simulation. If you go to what EHT could do, they look pretty much the same. This here is a boson star. This is one which does not have an horizon. It still has a shadow, but that shadow actually is a reflective shadow. So the light is not disappearing in the event horizon, the light is reflected. So actually looking back at the universe. So actually in principle that shadow should be filled with radio emission from the rest of the universe or individual sources. So that's a way to distinguish it. What we also found is by running the simulation, the shadow itself looks different to a black hole. But what's most important, we found it cannot produce a jet because the gravitational potential was different, so it would not produce a jet going out. And so that's something that you could not use to explain M87 based on a different argument. Of course, the future goes to the galactic center. From gravity, they have measured with the optical near-infrared interferometer. The star is very precisely going around, so we have the mass much better nailed down. And so you can do much better tests by using the galactic center, which also has a point source. Now, the problem with the galactic center, just to be quick here, is that the source is 1,000 times more variable. Yeah, so there are 20-minute flares where light goes around the black hole in 20 minutes. That would take like 2 weeks, 2 or 3 weeks in M87. Right? So in one day, M87 is pretty stable, while in the galactic center, we have many flares going around. So that's one thing. We also have scattering. This is a moving scattering screen in between us and the center of the Milky Way, which will actually blur the image, and that will change from a few days to the next. Within 1 day, this will be constant, but from 1 week to the next, it will also change. So what you have to do is, if you have an original image, this paper here that we published with Rudolph et al. In 2016, predicting what you see for actually the same year as we did the M87 prediction. It's much harder for the galactic center because of these two effects, the variability and the scattering. So for a single epoch, you would just expect something which looks very, very ugly. And then after integrating, you could actually find here we call first an ugly and then a beautiful peanut to see, but which again can fit to the GRMHD simulations and then do the same as for M87. But you have the mass fixed, and so that's a big, big important difference. It could also be, this was for a certain inclination angle. Recently, gravity predicted that the source in the galactic center would also be much more face-on. This was sort of more edge-on calculation. If it's more face-on, then the ring will become much more symmetric. And so that would actually make it easier again. So we have to see what the orientation of the galactic center is, and so we'll work on this in the next couple of months. What are the other upgrades? 2019 we did not observe. Alma didn't give us time for M87. We didn't go through the time review process, time allocation process successfully. Plus, LMT wasn't ready, and some other telescope had some issues as well. There are some upgrades. This is still planned. Kit Beak is now ready. The Greenland telescope is ready. Noema is now ready. So we have a few more telescopes. In particular, those two will be very important for M87. So we have much improved images in 2020, provided the weather is good. Okay. So it doesn't. Of course, by having more telescopes, the chance of having some of them at least in good weather is also increasing. So it could be that in the end 2020 is as good as 2017, but we have more bandwidth also, double bandwidth. So we'll have to see. For the galactic center, however, Greenland cannot see the galactic center. Noema can see it for 2 or 3 hours. It's still low elevation. There's all of Africa still missing. We need telescopes in Africa to expand the array to do the galactic center better. LMT is very crucial. If that's missing, we can almost forget it. And it had some issues recently. Our plan is now to put at least one telescope, it could be 3 or more, into Africa. The concrete plan that we're working on right now is to actually move the CEST telescope, the Swedish-European submillimeter telescope, which is in Chile, and which was the prototype for the Noema array, for the Plateau-de-Buhr interferometer. It's exactly the same design as the telescope they're still building right now near Grenoble at the Plateau-de-Buhr interferometer. So all the technical know-how is still there. All the manufacturers with some of the parts that you need to replace are still there, most of them actually in France. And you could then have a telescope here in the southwest of Africa. This is sort of exactly underneath the center of the Milky Way. You'd go to the second highest mountain in the southwest of Africa, in Gamsberg, which happens to be the property of the German Max Planck Society, because, believe it or not, this was studied and actually successfully studied as a site for the VLT. Right? It could have become the site of the VLT. And then you could actually get, and this is again for edge-on, you could get actually quite nice ring-shaped for the galactic center. Now, if you want to go further, you actually want to go into space. You want to go to higher frequencies, you want to go to longer baselines, and you want better UV coverage. UV coverage, the distribution of telescopes in the Fourier plane. And this is a concept that we've just published. The idea is to have 3 satellites. You could also have more, but 3 is actually quite good. Small satellites, 4 meters or so. We can put them into one launcher. You don't have to unfold them, which is always technically very expensive. And you put them on slightly different orbits, slightly separated from each other. And that means the inner one will actually drift a bit faster. They'll start together, they slowly drift apart. And then you'll get and in 4 hours they'll drift together once around the Earth, and roughly still the same baselines. So you get a short baseline at all orientations, and then they slowly drift apart, so you get actually all separations as well at all orientations. These are the so-called UV plane here. This is sort of these relative baselines, and you see how the relative baselines from short to long fill the entire plane. And that is now no longer an optical mirror that's scratched everywhere. That's an optical mirror that's perfect everywhere, because you measure all the Fourier component of the image. And so if you do this, you can actually make images like that. These are here, so the model. This is the 230 gigahertz model. It's 690 gigahertz. You still see it's scatterbrod for the galactic center at 230, but 690 you get really, really sharp views of it. You average them. You get here the average image of 600 or so gigahertz at 230 gigahertz, and then you run this through a simulated EHT observations. And we haven't done much image processing, so we're probably not doing good service to the EHT here in this respect. We can probably do better. But if you do it from space, you get all the fine wisps and structures here. So it's, and that should allow you to distinguish between at least some of these non-standard models that we have. Actually, I'm looking at the wrong clock there. So this always says 1:45. So I thought I had to wrap up, then it was slowing down again. So let me just finish here. And of course, the question is, how fundamental is this? What are we seeing? We are probing near horizon structures. We're literally within the theory of within GR. If you follow the light rays, your light ray is ending in the event horizon. Of course, you don't see anything there, but that's the point, right? You don't want to see anything there. So the fact that there's a shadow is very important. It's a combination of coming from the metric, from the light bending, plus the absorption in the event horizon, okay? Of course, you can always mimic things, right? You can have things which are slightly larger than event horizon, which also almost look like it. So in the end, it's always, as always in science, you're always only going to make a statement within a certain error bar. But we can already say that our object has a non-radiating surface which is smaller than the photon orbit, so 1.5 times the Schwarzschild radius. And probably, we haven't quantified it exactly, but we can make that limit even stronger in the future. And the question is, how does it compare to what gravitational waves measure? I think it's highly complementary and important. If you look at gravitational waves, you have stellar mass black holes, typically within a few tens of solar masses. So a range of 10 really in mass. And we measure supermassive black holes over 3 orders of magnitudes from the galactic center to M87, so 3 orders of magnitude. That's important because GR is a scale invariant theory. Everything you should do should work for a stellar mass black hole. It should work for a billion solar mass and a billion solar mass black hole. Many theories will go out of the window if you do this. Of course, gravitational waves do many sources, but they only have one measurement. We have 2 sources, but we have many repeated measurements. So we can do the same thing very precisely over and over again. And I think that is also very complementary. In the gravitational waves, you get many parameters from the waveform. We get parameters from the EHT, but we also have multi-wavelength observations. For example, the mass we can really determine independently, very precisely from the stars in M87, and particularly in the galactic center. Also the power of the source, the orientation, there are independent measurements here. So that is really, the multi-wavelengths is quite crucial here. And then, in the gravitational waves, most importantly, the event horizon and the metric signature on this scale is actually encoded in the ring down of the signal. And it also depends on the theory of gravity you use. It's actually relatively complicated to calculate. And this part has not been measured with high signal to noise at this point. And actually, it's also, as I said, most of this ring down is actually also generated at the photon orbit, quite interestingly. This is physically, that's what's happening. And the same is true for us. EH metric signature is we see the metric and the event horizon signal in the shadow. It's also dominated by the photon orbit, the same scale more or less. And we have I think more than 10 sigma detection at this point. Of course, we want to do better in the future, and we can do better. And combining all of them, I think, will give us a really nice view onto GR, and it will, I think, constrain many alternative non-standard parameters of GR in a very interesting way. So let me summarize. EHT has seen a black hole shadow. The mass we measure is consistent with the derived from stellar kinematics. Size, shape, structure, they all fit the prediction of GR. You can never confirm a theory, you can only try to exclude it, right? We cannot exclude GR at this point. It works perfectly fine. We have a really nice comprehensive set of tools. We have more images to come. Sag A star will become very important, and I think we'll be able to make very detailed tests of GR in the future. With this one, we also have pulsars with the SKA. We'll have gravitational waves. I think it's a golden era for studying GR and theories of gravity. Thank you.
Okay.
My apologies. I was always looking Q2. I thought I had still 50 minutes to fill. So
it's fine, and thank you. So time for questions. Yes.
Actually, two quick ones, since it is so fascinating. One is that I noticed most of the publications pushed the contrast so that it looks black in the middle, but what is actually the ratio?
Yeah, 10 to 1. 10 to 1. We have a 50 to 1 dynamic range, and the one that we can constrain is 10 to 1.
10 to 1.
But we cannot measure the width of the ring very well, and so, yeah.
And the second is, if in the early estimates and models you showed dramatic effects from the spin, how come it's almost nothing now, going from almost extremal
That's
to...
what I've been saying for 20 years, but people don't listen to me. Now, that's exactly for this reason I explained in the beginning, that the spin is, the width of that ring is not very spin dependent. From wherever you look at the black hole, you always get this effect of this circular photon orbit. You always have the shadow. It's always more or less the same size. That is, we measure the size very well. The spin itself is going to be on a very more subtle effect. And so we need to sort of combine this with, it's also orientation dependent, right? So if you look from face on, it's going to be very circular. Yeah, if you look edge on, it's going to be very edgy. So we're very one-sided. Unfortunately, M87 is very face on. So things become naturally much more circular. So would it have been edge on, we probably would be able to much better constrain the spin, because then it depends really on a short-shell black hole seen edge on will still be a ring. Right? A spinning black hole will be sort of one bright blob here and a very faint thing here. Yeah, so, but on the other hand, had M87 been an edge-on object, would have seen just a blob on one side, would not have been as interesting. So I'm happy that it's face-on now, and now we can do for Sag A star, maybe we can do a spin better on Sag A. Again, the variability, if you can make movies, that should also imprint some spin signatures in there. Yeah, it's a bit more work that needs to be done.
Perhaps a quick question. How do you compare your models with the data? I mean, I guess you just don't look at the picture, but...
Yes, that's actually an entire paper 6 dedicated to this. You take those snapshots and you just look at, and you calculate what the visibilities are. You make the Fourier transform and you look at what really is the measured data. Yet you compare, that is a chi-square minimization. But then you also need to do an ensemble average, so to speak. You have to run all your models from your simulation and fit them all and see what is the systematic variation each model has relative to a certain state. Trying to fit a model of the cloudy sky. You take a picture of the cloudy sky, you have a model of cloud generation. Not a single picture will perfectly ever fit. Yeah? But you have small clouds or you have large clouds and so forth. So you have to fit many individual snapshots and see sort of what is the distribution in chi-square you get. And then for every snapshot that you take, compared to the real data, you say, okay, I get that chi-square. It will never be 1. It should always be off, yeah, because you never predict the cloudy sky perfectly. But is it off so large that I can rule it out, or does it still fall within the variation of the turbulence there is? Sorry? Well, and that's the point here. At this point, we cannot even rule out, for example, different spin models. Yeah, we can. Some models are so bad, right, that even with any reasonable variations in turbulence, they would never fit. Those we can rule out. Many others will still survive. We could rule them out if we would be a bit less conservative based on, for example, the power of the jet or the large-scale structure, or this SED. We haven't done that yet. We try to be very conservative. So we looked at which models can we rule out, and a lot of models survived. I'm pretty sure many of those models we could also shoot out. But we try to be conservative at this point. Okay. Yeah, I think this is again an entire talk, actually. Sorry for the long answer.
Hello. You have a big collaboration, big instruments, you do big science based on big data. And we all know here that data processing is very important in these experiments. However, when we look at the press coverage, it's rarely talked about. Of course, the press, for the large audience, will focus on the final results. But it seems to me that for the first time, maybe, there was some significant coverage given to the people doing the algorithm, to data processing and so on. And I would like to know if this is because you have pushed from the PR point of view, there was some special effort made to emphasize this part of the work, or if you have any comment on that aspect.
Yeah, this is a very sensitive topic, how this came about. Some of that had to do with the political situation in the US, I think. The algorithms, we put a lot of effort into testing different algorithms. As I said, multiple algorithms were used. The one particular algorithm that was featured in the press was not used. This was the wrong information from MIT. That's all I can say. But the people that have been involved in this, all the people, there are lots of people involved, and the people that have been in the press have done fantastic work, but not for what has been said. Yeah, but it's good that the fact that algorithm development is very important. That's true, and we spend a lot of effort on it. Is it large data, big data? I think there is. Yes, we started with 3.5 petabyte, but actually the correlation process, something that has been well established in the VLBI community for ages. Some of these algorithms have been around for ages as well. But indeed, we go from 3.5 petabytes to 100 kilobyte in the end, right? The final image is about that size, or less. Yeah.
I know that wonderful talk, thank you.
Yeah,
and M87 is a beautiful image, but I was wondering, and I know that the Galactic Center was also measured in April 17.
Yes.
So what happened to the data, and how does the image look like?
I've seen the image.
Or is that too sensitive?
No, I mean, what we've done actually at the same time, we made images of both sources, and one just looked so much nicer and easier than the other that we said we have to put all our efforts onto M87. I mean, I've shown you simulations of what to expect. And if you just do, I mean, the first run, and the point is there's clear variability. There's clear variability in the data sets we have, which is very exciting. But now we have to use those algorithms and tools to actually, use that variability for information. And we have to just, refocus now on the source. We didn't do anything on Sagittarius. We made this first image, and then we did, M87. And now we have to spend a year, I think, on. I think our director promised a paper by the end of this year. I don't think so. I think we'll take a little longer time to.
I mean, does it look like the model?
Sorry?
Does it look like the model?
Does it look like a what?
Model.
That looked like the model. I can tell you. No, seriously. I mean, we really looked at it very briefly, yeah. No, I can't tell you.
You mentioned
clearly M87 was so much easier and nicer. So that's so.
You mentioned that the mass derived from the gas is not consistent with the one you derived from.
I think I said marginally consistent. So at best, marginally consistent.
What is the origin of the possible discrepancy?
If I were an expert on this, but the people, I mean, the simple answer is gas, is subject to many more effects than stars are, right? These are just gravitational point sources move around. The stellar kinematics, they actually had to take into account the dark matter component, for example, into their modeling. And it will be non-circular motion, non-gravitational forces that could change gas dynamics. And that is sort of some systematics that you have to take care of. Maybe some warping, I don't know. I mean, you have to do a decent modeling of the entire galactic potential and the black hole to get that value. And the stellar kinematics people tell us that, you know, of course they tell us, you know, we've done a better job, but you know, who am I to judge?
Okay, thanks for the excellent talk. Going back to the gas, you mentioned the problems of the coupling of protons to electrons, the heating of the gas and so on, the ADAF models, these are still open issues. So my question is, from your work, from your results, from your simulations, did we learn something more about the physics of the coupling of protons to electrons, the accretion disk and so on?
Yes. The official answer is no. And again, because you know, we ran, in fact, a range of, we defined a parameter R, which actually defines this proton-electron coupling. And if the parameter R is low, you're essentially disk dominated. You only see the disk. And if the parameter is high, you see it jet dominated. So our jet model that we had published in 2016 was highly jet dominated. But turns out that we can still fit most of the images with, you know, low R and a high R. Very low R is not going to work, but you know. But what we did not do is we did not check whether those models also can explain the entire spectral energy distribution of the entire jet. And I know for a fact that some models we still claim are reasonable will not work if you look at the entire SED of the jet. So at this point we have not yet learned about this, but I'm pretty sure we will. And it's pretty clear if you do a 7mm image, for example, you cannot do it with a low R. You have to have, you know, you have to have that magnetic electron coupling effect present. Whether it's already present at the ISCO, that's a question. It could very well be that this electron heating develops as you go along the jet. Again, this was a long answer, sorry. Because it's, again, an entire paper written on this, more or less.
Okay, let me ask a final question. What are the prospects for, or when will you be observing at a second frequency? And what physics do you expect to come from multi-frequency?
Oh yeah, good point. Actually, we have done first fringe test at 345, which looked actually pretty good. The problem is that the weather is going to be a much bigger enemy at 345 gigahertz. Not all telescopes, and everything will be much harder at 345. You have higher resolution. That's the main thing. You don't expect the physics to change too much. You also have less scattering, so in principle it should be better, but then it's, you know, it's offset by the much worse atmosphere. The spectral index, I don't know whether it will tell you too much. Everything should be achromatic there. Maybe, you know, optical depth is still some optical depth effect, that you have slightly different illumination from different regions, so we look in different depths, so there should be some differences. So if you do detailed modeling, maybe that helps, but we haven't studied that systematically. Okay. Mainly the resolution, I think.
Good. So thank you again for our presentation.